We live in a neighborhood of 8 planets, hundreds of moons, and millions of asteroids, all locked into stable, interlocking orbits. On one of those planets, life has diversified into millions of distinct species. But 4.6 billion years ago, all of these structures were missing. There was no sun to provide light, no Earth to provide ground, and no moon to steady the tides. At that time, this region of the galaxy was nothing more than a solar nebula, a cloud of gas and cosmic dust spanning billions of kilometers, drifting in a deep freeze. Left alone, a cloud like this would remain static. Without an external nudge, the laws of thermodynamics dictate that this dust would never have coalesced into anything more than a cold, silent void. The nudge came from a nearby supernova. When a massive star reached the end of its life and exploded, it sent a shockwave through the vacuum that compressed our local dust cloud, forcing it to collapse under its own weight. That single external disruption broke the equilibrium. It set off a sequence of collisions and chemical changes that would continue, uninterrupted, for the next 4.6 billion years. As the shockwave forced the solar nebula to contract, the conservation of angular momentum took over. Just like a figure skater pulling in their arms, the shrinking cloud began to spin faster and faster. Gravity intensified at the center, pulling the vast majority of the cloud's hydrogen and helium inward, concentrating the mass into a single dense core. As more matter was crushed into the center, the friction between atoms caused temperatures to climb into the millions of degrees. Eventually, the pressure became so high that hydrogen atoms began to fuse into helium. This violent process, known as nuclear fusion, released a massive burst of light and radiation, marking the birth of our sun. The sun is the undisputed anchor of our system. It claimed 99.8% of all the matter available in the original cloud. Everything else, from the rings of Saturn to the water in your glass, had to be built from the leftover scraps. These leftovers formed a thin, rotating disk of debris orbiting the new star. Through the process of accretion, dust particles collided and stuck together. Over millions of years, these collisions built larger and larger bodies, eventually forming the protoplanets. This temperature gradient shows how the sun acted as a filter. In the inner orbits, the heat was so intense that volatile gases and ices could not condense, leaving only materials with high melting points, like rock and metal. This physical constraint is why the inner solar system is populated exclusively by dense, rocky worlds: Mercury, Venus, Earth, and Mars. Past the frost line, where temperatures dropped, gases like hydrogen and methane could finally settle. These materials clumped together to build the massive outer giants: Jupiter, Saturn, Uranus, and Neptune. The composition of each planet was determined by its distance from the heat. In this way, the architecture of our solar system was a direct consequence of thermodynamics. Roughly 4.54 billion years ago, Earth was a molten sphere, heated by radioactive decay and constant asteroid impacts. Its development was interrupted by a Mars-sized object, known as Theia, which was pulled into a direct collision course with the young planet. The two bodies collided at several kilometers per second. The impact released enough energy to liquefy both objects, and Earth's gravity ejected millions of tons of its own rocky mantle into orbit. This ejected debris didn't escape into space. It became trapped, forming a ring of glowing rock circling the Earth. Gravity pulled the debris together within the ring, and in a relatively short period, those fragments coalesced into the moon. This collision was more than a destructive event. It was a structural necessity. The moon's gravity stabilized Earth's tilt, preventing the planet from wobbling wildly and creating the climatic stability required for life to take hold. As the era of heavy collisions slowed down, Earth began to radiate its heat into space, allowing the surface to cool and harden into a solid crust. Steam in the atmosphere condensed and fell as rain for thousands of years, pooling into the basins to form the first oceans. Within these oceans, the same carbon and minerals originally found in the dust cloud began to react. Driven by the sun's energy and geothermal heat, simple elements bonded into complex organic molecules, eventually forming the first microscopic organisms. These organisms represent the first biological link in a chain that leads directly to every plant, animal, and human being alive today. Every atom in your body, from the iron in your blood to the calcium in your bones, traces back to the matter inside that original, silent gas cloud. This same sequence is likely repeating across the universe. Right now, in distant galaxies, other shockwaves are hitting other clouds, starting the same mechanical countdown toward new worlds. The birth of our solar system was a sequence of events, where each physical change, from a spinning cloud to a stable orbit, provided the specific conditions necessary for the next. To follow the rest of the story, subscribe for more journeys through the cosmos.